You add an index to fix a slow query. The query time drops from seconds to milliseconds. Huge win. But then you notice that your insert throughput has collapsed by a factor of 5, and write latency is spiking. That's the hidden cost of the B tree. Today we open up the index that powers almost every relational database to see why it's brilliant for reads and why it can silently destroy your write performance if you aren't careful. B trees have been the default on-disk index for decades. MySQL's InnoDB uses a variant called B plus tree. PostgreSQL uses classic B trees. They back primary keys, foreign keys, and any column you explicitly index. They give you logarithmic search time, O of log base B of n, where B, the branching factor, is usually hundreds. So a point lookup on a billion row table takes only 3 or 4 page reads. The tree is balanced and every node fits exactly into an 8 kilobyte or 16 kilobyte page. The upper levels are almost always cached in memory, so a typical read touches just 1 or 2 disk pages. Inside a node you find a sorted array of keys and a matching set of pointers. In internal nodes, each pointer leads to a subtree whose keys lie between the adjacent keys. Leaf nodes hold the actual data, either the whole row when the index is clustered, or a reference to the heap otherwise. In InnoDB, the primary key is clustered, so a lookup returns the full row straight from the leaf. When you execute a query that filters on an indexed column, the database walks from root to leaf. It compares your search key with the keys inside the node, picks the child pointer that covers the range, and repeats. Because the keys are sorted and the fan-out is huge, often several hundred per node, you cross only 3 or 4 levels even for a billion rows. That's logarithmic scaling, and it's why reads stay fast as data grows. The algorithm is simple. You walk the keys in order, compare, branch, and recurse. In a real engine, the comparison is done with binary search, perhaps with low-level optimizations, but the logic is exactly what you see here. This simplicity is what makes reads so efficient. No locks, no ordering troubles, just a handful of page accesses. Now insert a new row. The database finds the leaf where the key belongs, just like a search, and inserts the key into that node's sorted array. If there's room, you're done. 1 leaf page right. But if the leaf is already full, you must split it. A split creates a brand new page, moves roughly half the keys to the new page, and inserts the middle key into the parent, along with a pointer to the new sibling. If the parent overflows, you split it too, and the cascade can climb all the way to the root. A single insert can trigger a chain of page splits, writing multiple pages to disk. Databases use a fill factor to control this. PostgreSQL's default for B trees is 90%, meaning a page is considered full when it's 90% packed. With a lower fill factor, you leave free space, so pages can absorb several inserts before a split is needed. But the worst write amplification happens with random key order, when you insert keys that don't arrive sorted. Each new key is equally likely to land in any leaf, and once a leaf is full, it splits, scattering the new pages across storage. That's when write amplification can easily hit 3 to 5 times, each logical row causing 3 or more physical page writes. Your IOPS budget gets eaten long before the disk's raw throughput is reached. Updates add even more pain. If you change an indexed column, the database has to delete the old index entry and insert a new one. Double the index work for a single row change. In PostgreSQL, an update always creates a new row version. Unless the heap-only tuple optimization can skip the index gets a new entry immediately. Frequent updates on indexed columns can bloat the index dramatically, and the stale entries linger until vacuum cleans them up. This is why you should think twice before indexing columns that change a lot. The code we just saw is a toy, but it captures the essence. Find the leaf, insert, check capacity, and split when full. The caller then merges the new page up the recursion. In a production engine, you'd add concurrency control, write-ahead logging, and multi-version machinery. But the extra write overhead from splits is the real performance killer at scale. Let me share a real story. A few years ago, I worked on a system that stored user-generated events. The table had about 200 million rows, growing by tens of millions per day. The primary key was a random UIDv4, chosen for application-side uniqueness. Inserts peaked at 1800 per second, and reads were rare, mostly occasional full-page queries. We added a couple of secondary indexes to accelerate an admin dashboard. In staging, the queries got fast. Then we deployed, and within 10 minutes, insert throughput fell to 350 per second. Latency spiked from 3 milliseconds to 18, and the app started dropping events. The cause wasn't the new indexes alone. It was the combination of a random UUID primary key and the B-tree's nature. Every new row landed in a random leaf page. As more and more leaves filled up, random splits became a constant background noise. Write amplification shot up. We saw disk writes 4 times higher than the log would suggest. The storage IOPS were completely saturated, even though raw throughput was still under 10% of the disk's bandwidth. We fixed it by replacing the primary key with a monotonically increasing integer, which let inserts append to the rightmost leaf with minimal splits, and we replaced one of the secondary indexes with a Biran index for the timestamp column. Write throughput recovered to 1700 per second, and latencies returned to normal. The lesson: with B-trees, the key order matters as much as the number of indexes. A random key can turn a perfectly fine insert workload into a split hurricane. So B-trees shine on read-heavy workloads where you need low latency lookups and ordered range scans. But when writes dominate, alternatives like LSM trees, which power RocksDB and Cassandra, become attractive. LSM trees buffer writes in memory and flush them as sequential files, avoiding random page splits entirely. The trade-off is that reads may search multiple sorted files, and background compaction adds I/O, but writes are orders of magnitude faster. For sequential, write-only data, event logs, sensor streams. You can even go without a B-tree and use a Bren index in PostgreSQL, which summarizes block ranges and costs almost nothing on insert. Specifically, avoid B-tree indexes on columns that are updated extremely frequently, like status flags or counters. Also, for append-only data with strictly increasing timestamps, a B-tree on the timestamp column will still work well, because sequential inserts target the rightmost page and splits are cheap. But if concurrency is extremely high, even that single hotspot can become a bottleneck due to latch contention, not because of splits. That's another problem entirely, but the solution might be the same. Consider a Brin index or partitioning. You can tune write overhead inside an existing B-tree by lowering the fill factor. Setting it to 70 leaves the 30% of each page free, which can absorb a lot of random inserts before a split. The cost is larger indexes, about 30% more disk space, but that's often a good trade for stable write throughput. In PostgreSQL, you can set the fill factor, both at the table level and per index, via the fill factor storage parameter. You also need to monitor what your indexes are actually doing. Look at the usage counters in your database's index statistics view. If an index has 0 scans after weeks in production, drop it. It's only wasting write capacity. If the count of index entries fetched is high while the number of table rows read is low, the index is pulling its weight. More important, watch the disk write metrics. If you see write operations far higher than the number of rows inserted or updated, your indexes are amplifying writes. That's your signal to reconsider the index design. So here's the rule of thumb. Every B-tree index you add increases write cost. For an index with a naturally ordered key, like an auto-increment integer, the overhead is often modest, 1 or 2 extra page writes per row. But for a random order key, the write amplification can quickly exceed 3 or 4. If your application generates random identifiers, consider using a key that sorts naturally, or use a different storage engine. Measure your write amplification in production. If a single logical row insert causes more than roughly 2 to 3 physical page writes on average, your indexes are hurting you, and you need to act. B-trees remain the backbone of relational databases for good reason. They give predictable, fast reads. But that speed comes at a cost every time you write. Understand how your keys are distributed, tune the fill factor, and be ruthless about keeping only the indexes you really need. That's how you get the read performance without the write disaster. Thanks for watching. I hope this one was useful. See you in the next video.